You've been told bigger batteries are the future, but what if that's completely wrong? What if the real breakthrough isn't more kilowatt hour, but how tightly energy is packed? Everyone is chasing faster charging and longer range, but China quietly solved a much bigger problem most people don't even know exists. When people talk about EV batteries, they almost always talk about kilowatt hours. Bigger numbers, better car. Simple, right? But that way of thinking is outdated and it's holding the industry back. Because two batteries can have the same kilowatt hour, cost the same, charge from the same charger, and perform completely different in different real world experiences. The difference comes down to energy density, and this is where China just pulled ahead. By the end of this video, you'll understand why engineers care more about watt hour per kilogram than total kilowatt hour, why this changes charging, cost, safety, and cold weather performance, and why the rest of the world is now trying to catch up. And there's one uncomfortable truth most EV marketing avoids. We'll get to that as well. Let's start with the problem. Energy storage has always been a trade-off between four enemies: weight, size, heat, and lifespan. For years, battery makers solved range anxiety by doing the laziest thing possible. They added more range. They added more cells. That works, but it creates new problems: heavier cars, worse efficiency, longer charging times, higher material costs, and more heat under fast charging. So engineers ask a harder question. What if we didn't add more batteries? What if we made each kilogram store more energy? That question leads directly to energy density. Energy density is simple: how much energy you get per unit of weight or volume. Gravimetric energy density is measured in watt-hour per kilogram. Volumetric energy density is watt-hour per liter. Think of it like packing a suitcase. You can bring more clothes by using a bigger suitcase or by folding better. The West mostly chose the bigger suitcase. China focused on folding better. Here's something most people don't realize. A 75 kilowatt hour battery with poor energy density weighs more, needs more cooling, charges slower at high power, and loses energy as waste heat. A 75 kilowatt hour battery with high energy density weighs less, stays cooler, holds peak charge power longer, and costs less in materials. Same kilowatt hour, totally different behavior. This is why engineers roll their eyes when marketing says just add more range. Traditional lithium-ion cells, especially older design, hit a wall around 240 to 260 watt-hour per kilogram at the cell level for mass production. Pushing beyond that created problems like unstable chemistries, faster degradation, safety risks under abuse. For the long time, this looked a hard ceiling. Many companies accepted it. China didn't. Here's the first key insight. China didn't win by inventing a magical new chemistry overnight. They won by stacking many small engineering improvements into one system. Things like thinner current collectors, higher silicon content in anodes, improved cathode structural crystals, and better electrolyte additives. Each change alone looks boring. Together, they break the ceiling. Here's where it gets interesting as well. Most people talk about cell energy density. Engineers care about pack level energy density. Older battery packs waste space. Modules, brackets, bolts, air gaps, heavy casings. China aggressively removed those. By integrating cells directly into structural packs, you get fewer materials, less dead volume, lower resistances, better thermal paths. This alone can boost usable energy density by 15 to 25% without changing chemistry. It's not a magic, it's just brutal optimizations. Why this changes charging? Higher energy density means less mass per kilowatt hour. Less mass means lower internal resistance, less heat buildup, slower voltage rise during charging, and these all help, and that's the secret. Charging speed is limited by heat, not charger power. If your battery stays cooler, it can hold high power longer. This is why two batteries on the same charger can have very different charge curves. Heat is the enemy of the batteries. Every amp flowing through resistance turns into heat. More materials and longer current paths equal to more resistances. By increasing energy density, you get current paths that get shorter, fewer parallel connections are needed, and thermal gradients shrink. This directly improves fast charging stability and cycle life. In simple terms, dense batteries don't just store more energy, they waste less of it. Here's a common fear: higher energy density means more dangerous batteries. That's only half true. Poorly designed high-density batteries are dangerous. Well-designed ones can be safer. Why? Because fewer cells, fewer wells, fewer connectors, and better thermal control reduce failure points. China invested heavily in abuse testing, nail penetration tests, thermal propagation barriers. Safety didn't come from chemistry alone, it came from systems development. Why this matters for cost? Energy density quietly attacks cost in three ways: materials, manufacturing, and logistics. Higher energy density means fewer raw materials per kilowatt hour, less aluminum, copper, and steel, lighter packs to ship, and fewer steps in assembly. This is why cost per kilowatt hour keeps dropping even when raw material prices fluctuate. It's not magic pricing, it's engineering efficiency. In cold temperatures, batteries suffer because of internal resistance increases, voltage drops faster, heating systems consume energy. In high energy density packs, they warm up faster, retain usable voltage longer, and waste less energy fighting resistance. This doesn't eliminate cold loss. Physics still wins, but it narrows the gap. Now for the uncomfortable truth. Higher energy density usually means tighter margins for error, stricter manufacturing control, and higher upfront R&D costs. This is why not everyone can copy it quickly. You don't just change chemistry. You change factories, quality control, and supplier chains. That's the real barrier. Why this is hard outside of China? China controlled much more of the battery supply chain: mining, refining, cathodes, anodes, electrolytes, cell assembly, pack integration, all of this. That vertical control allows faster iteration, tighter feedback loops, quicker scaling. Elsewhere, companies depend on fragmented suppliers. That slows everything down. People love to say solid state will fix it. Maybe eventually. But today, solid state batteries will struggle. But today, solid state batteries still struggle with high internal resistances, poor low temperature performance, manufacturing stability. Meanwhile, liquid lithium ion keeps improving. Incremental wins beat theoretical promises. Energy density affects more than range. It changes charging station throughputs, grid load smoothing, vehicle efficiency, and life cycle emissions. And at the end, you'll see the impact on the total ownership costs. When batteries get lighter and denser, everything downstream improves. That's why engineers obsess over this metric. So, why kilowatt hour is the wrong question? Here's the key moment. Stop asking how big is the battery pack. Start asking how efficiently is energy stored, moved, and protected. Energy density is the quiet lever that controls charging curves, heat, lifespan, cost, and safety all at once. China didn't win by chasing bigger numbers, they won by understanding the system.